Okay, so welcome to the class on regression, and we're going to start off with kind of a very simple example. So we have this kind of scenario where we're trying to predict movie revenue from social media buzz, and this social media buzz, which we're going to put here on the x-axis, is going to be the tweet rate per hour. And on the y-axis, we're going to have the opening weekend revenue. Now, of course, if I want to predict movie revenue, I'm probably going to use a lot of different information. But for the moment, we're trying to predict it just on this measure of social media buzz. And of course, the idea is using this, we can help plan our advertising campaign for our movie, try and maybe force it onto more screens, etc., etc. So let's just say we have some points here. And generally, more buzz, the more revenue a movie's going to get. But this relationship is not actually going to be perfect. We're going to have something like this. And then what we're trying to do with regression is we're trying to draw a line that best fits the data. Now, if I had good artistic skills, that should actually be a straight line. And let's just kind of add one more thing. Let's do it in green. Let's just have the average movie revenue, which we're going to call Y bar. And for a given X, the individual prediction, so this is my prediction, is going to be Y hat. This would be my Y, and then the difference between them is going to be my error, which we sometimes denote with the Greek symbol epsilon. Okay. So this line kind of has, basically, this is the regression line. This contains all the Y hats. Now, the equation of the regression line I'm just going to put it here, is going to be Y hat, and that's basically my predicted Y, equals beta 0 plus beta 1 times X. Now, sometimes we'd actually put, this is the fitted version, so we can put hats on the betas as well. This is just saying we've built this model now, and we've created this regression line. Now, what do these guys mean? Well, the beta hat 0 is basically just the intercept. And in this particular example, this is kind of the revenue where X equals 0 or has no buzz. Now, quite often you're not going to have a Y with 0X. It's kind of outside the range of the data. With regression, as you get better predictions as you move to the center of the data. But this is the interpretation here. This is the revenue at X equals 0. And the beta hat 1 is basically the increase in revenue for each additional unit of X. In this case, tweet rate per hour. We call it tweet rate per hour. So if tweet rate per hour goes up by 1, then the revenue is going to go up by this value of beta hat 1. And a few of the things we're actually going to use. So just imagine for each of these points, we have some sort of error. You get it? Now, the idea is we draw this line to minimize the errors. We don't want our regression line, you know, flying off here somewhere, because otherwise there'd be huge, huge errors. So basically, what we're going to do, and I'll just write this down, with regression, we have the sum of squared errors, which, say, for example, if we have n points, so in this case it'll be n movies, it's going to be each individual y minus y hat I squared. Why do we need to square it? Because if we didn't square it, everything would just cancel out. So this is just like a measure of the magnitude of the errors. We also have the total amount of variation in the data, which is I equals 1 to n. And this is going to be yi minus y bar minus the mean value squared. So this is just like when you calculated the variance in business stats. This is all it is. Now let's just move down a tiny bit, make it a little bit bigger. And then finally we have our S. This is all in the notes. So just kind of, I just want to kind of motivate it a little bit. The sum of squared of regression equals I equals 1 to n. And this is going to be my y hat I minus the y bar. And that's just the amount of information contained in the regression. So that's kind of these values here make up the sum of the squared of the regression. And funnily enough, the sum of squared total equals the sum of squared regression plus the sum of squared error. So let's kind of actually just implement this now in R. Okay, so we have some data here. This is from the notes. And this is my data on the tweet rate. So let's just load it in. And let's just see what's kind of in there. And you can see here that we have two columns, the tweets per hour and the revenue in millions. Let's just view. So here we go. We've got the tweet rate per hour and we've got the revenue in millions. And as you can imagine, these guys are pretty much related. We have higher tweet rates per hour and we have a higher degree of revenue. So let's run this regression. I said all this regression is doing is, when I did all the kind of the mathy slide, all we're doing is minimize, we're trying to position this line in order to minimize the error. So all we're doing is we're trying to fit these lines to make the red lines as small as possible. That's kind of the non-mathy way of explaining it. So how do we do this? Well, R has a regression command. And LM means linear model. Linear model, we're fitting a straight line, a linear line. To the left, we have the Y. To the right, we have the X. So it's very similar to those aggregate functions that we did in week 3, I think it was. So you give basically, this is called the formula, and then you describe the data, and then you give the data. So we call it, and then we get this. We get these actual values, which are the beta 0 and the beta 1. And we can actually make predictions from these guys. So let me kind of go back to our little whiteboard. Let's just download that a little bit. So we have, basically we have a regression model. And that's going to be my y. And this is just a regression model in general. Is beta 0 plus beta 1 x. Plus we know we're not going to be perfect, so we have this, which is the error. Now we run the LM, or run, and what we're doing is we're minimizing the SSE, which I talked about before. So after we've run the LM, we kind of get this fitted model. We get the fitted regression. This is the equation. This is what we call the equation of the regression line. Okay, so what do we have here? Okay, we got 1.15015 and we got 0.00787. Okay, so let's go back to our little thing. So now we have, so let's just have a scenario. So what is the revenue for a movie with a tweet rate per hour of, which I'm going to put in brackets, tweet rate per hour equals 100. Well, my predicted revenue is beta hat 0 plus beta hat 1 times x. We found out from LM this was 1.15015 plus we have 0.07877. So this is my regression coefficient of my slope, and we have an x of 100. And add them all together, and we get a prediction of $9.207 million. This would be. So that's how we do regression to make predictions. Now we can do this in R as well. So what I'm going to do is I'm going to create a new data frame. And it's just going to have the X in. It's really important here that we actually have all three values just in one column. This is the tweet rates per hour. And now what we're going to do is we're going to predict. So we have our tweet rates per hour, and we're now going to predict. The predict function takes the model and it takes the new data and it makes some predictions. So let's print what these predictions are. And so for kind of 50 tweets per hour, we've got this. 100 tweets per hour, our predicted revenue is 9 million, but 1,000 tweets per hour, our predicted opening weekend revenue is 80 million. So you can see this linear relationship here. As we increase the tweet rates per hour, we have much higher revenue. Okay, so that was like the little introduction. I want to just do two more things in this video. Now, we can have confidence intervals and we can have prediction intervals. So let me just explain what each of those are. So we all remember what a confidence interval is. So, and we're not going to do the math here, we're just going to do it in R. Because the math actually, particularly when you get to multiple regression, which is like lots of regression, kind of independent variables, then the math gets very, very complicated. So if 100%, 1 minus alpha confidence interval. Now this is actually for the regression line. So given an x, this is actually for the regression line at that point. Now, the prediction interval and in a way, in a business sense, this is actually the most useful. So, given x, this gives a prediction for the individual movies. So, say if we have a tweet rate of 100 per hour, my confidence interval is basically that regression line, how we think that regression line varies. The prediction interval is when 90, say for example alpha equals 0.05, that would be a 95 prediction interval for how much that movie would make in the opening weekend revenue. So this second one is a tougher task. So this guy is going to be wider and this guy is going to be narrower. Two other things for both of these guys, it's kind of important that these tend to be narrower near the center of the data, which makes sense. Because you have a lot more information there. You know, if I've got a lot of movies that have a, making between maybe $50 and $100 million for the opening weekend revenue, I'm probably going to have a fairly accurate predict them. If I'm trying to predict maybe Avatar 2, where I've only had 1 or 2 movies in that realm, it's going to be much harder to actually predict. So we can do all this in R. So this time, rather than just running the predict function, normally we're actually adding an extra thing. We're saying we want an interval, which is a confidence interval, and we want it at level 0.95. And if you remember, I think you all did pretty well on the exam, this will give you a 95% confidence interval. So we see for each of these values, we get the predicted values we had before, and then we get an upper and lower kind of confidence interval. Now note this is negative, Again, we've got a very low value. It's quite a hard thing to predict movies just from tweet rates. So we actually get this kind of nonsensical prediction there that it's going to be between -2 and 12. And then we have the 95% predictions. And again, you can see actually for individual movies, it becomes much, much harder. The best one here is we have this tweet rate of, which was actually the 1,000 one. And we have this predicted revenue of 80 million. But remember, 95% is quite wide. We feel the movie is going to have a revenue between 50 million and 110 million. As I said, again, this is a very hard task to predict movies based on only one piece of information. So we'll finish off this little video by actually getting more conceptual. Now, imagine I've gone to my boss at the movie company with this model, and my boss, she goes, you're an idiot. This is kind of useless. It's not accurate enough. There's lots of other things that you might actually be thinking of. Now, let's just have a look. So we have our Y, which is our movie revenue, opening weekend movie revenue. And then you'd have your X But now look, we call it x1. Now this is I've not really done this notation before, but this is our dependent variable. This is what we're trying to predict. And my x1, this is actually going to be my first independent variable, which is my tweet rate per hour. And my x2 is going to be, let's just say, okay, let's just have this the number of screens. That's going to be a pretty good predictor. Not always. I mean, you can have some blockbusters which are flops, but, you know, if a movie's on a lot of screens, then it's liable to be more popular. Number 3. We're going to have, let's just say, something to do with the star power of the actors. You know, whether they've been in lots of successful movies before, something like the previous success of the director. And we can carry on adding more and more variables. So we have x20, what the stars had for breakfast, which is probably pretty useful. Useless, I mean. And this actually gets us what we call a multiple regression model. And a multiple regression model is we have k predictors, so k independent variables, which are these guys here. Then we have y equals beta 0 plus beta 1 x1 all the way up to beta k xk with plus the error. Now here, and then we can actually fit them. So again, as before, we'd have the y hat. For the regression line. And I can't actually draw this on a piece of paper because this is basically, you know, we have 2 dimensions. If I had 2 independent variables, we have 3 dimensions. And here we'd have like k plus 1 dimension. So it's just, you'd have to imagine like the line I drew, but in an infinite space. And just what's very important for you guys is beta 0. This is the kind of predicted revenue. So it's still the intercept when all the x's are 0. And this, like beta I, we'll call it, is the increase in revenue, or the increase in y, when, let me just, xi is increased by 1. But we've got more than one xi. So what's it? So, and all other x's are held constant. So, you know, we're not interested. We kind of all we're interested in is how we, you know, x1 goes up by, say we're beta 1. When x1 goes up by 1, this is how much y goes up, assuming we don't increase the others. So this is what the beta coefficients are. And I think that makes a nice little end to the video.